Stability of cycloalkenes. Now, cycloalkenes are fairly stable once the rings get large. So when you have small rings, obviously small rings, even as alkanes, are unstable. But as alkenes, cycloalkenes are even less stable because now you're forcing even more ring strain to occur. So remember, these are sp2 carbons here and here. Let me make that a little bit bigger. A little bit bigger. Let's just get rid of that. There we go. So these are sp2 carbons. So sp2 carbons want to be 120 degrees as a bond angle. So the trigonal planar, they want to be 120 degrees. Unfortunately, when you're trapped in a small ring, a 3 or a 4 membered ring, your angle is much less than 120. So for example, here, these carbons are being forced to have a bond angle of 60. It's going to make these bonds very weak because they don't want to be stuck in a 60-degree angle. They want to be 120, so those bonds will be weak to accommodate that angle. Same thing happens here. Now you're forced to be 90 degrees when you want to be 120. Better than 60, but not as good as 120. So small rings as alkenes exist, they're just very unstable. Now as you get bigger, say the 5-membered rings, that's where they become more stable. But in 5-membered rings and 6-membered rings as well, these are by far the more common ones, the double bond can exist very, very simply, no problem. These are very, very common in nature, actually. The double bond has to be cis. So in 5 and 6-membered rings, the double bond must be cis. And in 7-membered rings as well, the double bonds are always cis. So 3, 4, 5, 6, and 7-membered rings, double bonds are always cis. At the 8-membered ring, now you can start to get transdienes. Only at 8. And that's because as the ring gets larger and larger, they become quote-unquote floppier. They get much more degrees of movement. You've already seen that small alkanes, cyclopropane, butanes, cyclopentanes, cyclohexanes, they're fairly rigid. They have some movement, but they're fairly rigid. But you did also notice that 3-member rings were extremely rigid. 5-member rings became a little more free. 6-member rings a little more free. As you get bigger and bigger rings, they get more and more freedom of movement. They can kind of flop around because they're bigger, right? As they get bigger, they have more freedom to move. Same thing happens in cycloalkenes. The rings get bigger, they have more room to move. So they can twist to become trans in an 8-member ring. Now, the truth of it is that they have to get into a cyclodecane for the trans double bond to be as stable as the cis. Because once you get to the decane, the big 10-member ring, they have so much room to move that it's almost the same as being a linear hydrocarbon. Almost the same. So the take-home message here is small rings with double bonds are very unstable. 5, 6, 7-member rings have to be cis, and they're fairly stable. 8-member rings can be trans double bonds. Most of the time they're cis. And once you get to 10-member rings, that's when you become able to have a trans double bond and be relatively normal in your chemistry. Now, Brett's rule. Brett's rule addresses the bicyclic compounds. Recall bicyclic compounds are these types of things here. Now, also remember that these carbons here are what are called bridgehead carbons. They're the carbons where the bicycle comes together, so they're called bridgeheads. In Brett's rule, or Brett's rule states that a bridge bicyclic compound cannot have a double bond at the bridgehead position unless one of the rings contains 8 carbons. So unless one of your rings is 8-membered, a double bond at a bridgehead carbon is not allowed. So for example here, this alkene actually exists. You can buy this one from the supplier. Not a big deal. This one, however, does not exist because the double bond is at a bridgehead and these rings are much less than 8. And that's Brett's rule.